Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. My name is Ibrahim Magdi Hussein Hassan Muhammad from University Technology Petronas. Today I'm going to present my paper talking about the pressure drop determination in a microchannel heat exchanger with a various protrusion depth. As seen at the content, I am going to present those outlines, the introduction, then the overview, then the methodology, then the resultant discussion, and at the end, of course, the conclusion. A heat exchanger is a system used to transfer heat between two or more fluids. Heat exchangers are used in both cooling and heating processes. The fluids may be separated by a solid wall to prevent mixing, or they may be in a direct contact. The configuration of a connection of riser to the main manifold has a great influence on the flow uniformity inside the microchannel heat exchanger. This research include investigation of the pressure drop effect on the flow maldistribution along a horizontal manifold of microchannel passages with various protrusion depth configuration. Characterization and analysis of the flow uniformity are to be carried out experimentally. This presentation in particular shows the experimental setup to conduct the experimental measurements, as well as the outcome result of the pressure drop along the microchannel heat exchanger with various protrusion depth. The microchannel heat exchanger has many important usages and application which are used in cooling of microelectronics, microstructure reactor for chemical production, used in medical researches, used in microelectro-mechanical systems as microheat exchanger, mixers, pumps, turbines, sensors, and actuators. Heat transfer in the microchannel heat exchanger is a function of a maldistribution of flow. The effects of protrusion configuration of microchannel passages on the flow uniformity were numerically studied so far. In addition, resources are limited. The effects of a various protrusion configuration and several geometric parameters on the flow uniformity can still be explored further. The knowledge of the effect of the aforementioned parameters and configurations are extremely useful in designing an optimized manifold of microchannel heat exchanger that could be yield maximum possible heat transfer coefficient and minimum possible pressure loss of the fluid. And can be concluded in 2 points that the efficiency of heat transfer process in microchannel heat exchanger depends on the flow uniformity. In the microchannel passages of heat exchanger with the various protrusion depth, the flow become non-uniform or maldistributed. This paper aims to present experimental measurements results and mathematical prediction results of pressure drop across the microchannel heat exchanger. Two identical prototypes of microchannel heat exchanger with a different configuration of protrusion have been considered in this investigation. The pressure drop measurements have been carried out with at various Reynolds number, varies from 1500 to 7500 by varying the flow rate. So the main objective is to implement an experimental measurement of pressure drop microchannel heat exchanger model with a bare case and with a protrusion case to suggest a protrusion configuration that yield the minimum degree of flow maldistribution among the considered protrusion configuration. The scope of the work studied the main principles and basics of microchannel heat exchanger, identify the effective parameters in terms of OD design and operation on the performance of microchannels, study the material selection and fabrication process to build a prototype of the experimental study and setup. The main research paper used at this study were focusing on microchannel heat exchanger, flow uniformity, microchannel heat exchanger fabrication, pressure drop inside the microchannel heat exchanger. As for the methodology, we have analysis technique, which consists of experimental setup, pressure drop calculation, pressure drop measurements. And for the process variables, we have protrusion configurations, flow rate, pressure drop, flow uniformity. And for the protrusion types, we have two protrusion types, which are bare case and protruded case, which is take the form of a curvy inside the header. As for the design, we have many variables as manifold diameter, d hash, outflow port diameter, dc, number of outflow ports, which is n here, then the initial velocity, v, and other some geometrical variables as the m, which is half the distance of the s, then p, and l is the manifold length, and n, as mentioned before, which is number of outflow ports, and of course the hydraulic diameter at the region where outflow occur. Then we have the sum of the coefficient of turning loss from the manifold into ports and the friction coefficient for the port flow. As shown here, the design parameter of the microchannel heat exchanger, as the header diameter is 5 mm, the outflow port is 1 mm, the length of the manifold of the header is 74 mm, the number of ports is 20 port, and the length of the port is 50 mm, and the channel spacing between one port to another is 1 mm. And as for the experimental setup, we are using the prototype of the microchannel heat exchanger. Second is the peristaltic pump, which is used to pump all the fluid inside the microchannel heat exchanger with different flow rates. And we are using the pressure sensors, which is the manometer, which is used to measure the pressure difference between the inlet and the outlet. And of course, the data logger to record the data. The graph on the left side of the slide shows the pressure difference gap of the curvy case between measured and predicted is very high. Same concept goes to the bare case, as the pressure difference gap is high between the measured and predicted one, as shown at the graph on the right side of the slide. However, comparing the pressure gap difference as measured or predicted for the curvy or the bare case is almost close, as shown on the previous slide at the previous graph. A disagreement between the measured results and predicted calculation is too considerable. They are increases as the flow rate or Reynolds number increasing. This could be explained that the actual channel diameter may be a bit smaller than the nominal diameter, or a header roughness maybe have a higher value than the nominal roughness value. At this part, we are going to present result and discussion. The graph on the right presents the measured results of the pressure drop across the microchannel heat exchanger of the two types of protrusion configurations, where the pressure difference between the two cases is almost close. The experimental and calculated results in the table show that the gap pressure difference of the two cases at the same flow rate or Reynolds number in total is not high, either measured or predicted. However, the calculated and the experimental pressure difference is always lesser in the bare case than the curvy case. Results are indicating that the bare case has a lower pressure difference than the curvy case at the measured results and predicted calculation, which is mean the flow distribution inside the microchannel heat exchanger of the curvy case is better than the bare case, based on that the pressure and the velocity are inversely proportional to each other. The graph on the left side of the slide shows the pressure difference gap of the curvy case between measured and predicted is very high. Same concept goes to the bare case, as the pressure difference gap is high between the measured and predicted one, as shown at the graph on the right side of the slide. However, comparing the pressure gap difference as measured or predicted for the curvy or the bare case is almost close, as shown on the previous slide at the previous graph. A disagreement between the measured results and predicted calculation is too considerable. There are increases as the flow rate or Reynolds number increasing. This could be explained that the actual channel diameter may be a bit smaller than the nominal diameter, or a header roughness maybe have a higher value than the nominal roughness value. This work can be summarized and concluded as the pressure drop in the microchannel heat exchanger is measured, calculated, and analyzed for two cases of protrusion configuration of the microchannels in the header, five different flow rates of five different Reynolds number varying from 1500 to 7500 Reynolds number have been considered at this work. These experiments and analyses are demonstrating that the typical friction factor correlation and local pressure drop coefficients couldn't be used to predict both the major and minor losses in the microchannel heat exchanger. For a particular conclusion can be summarized as the pressure drop in both cases of microchannel configurations, smooth and curved, indicate large difference gap between measured and predicted results. Based on the measurements results and prediction calculations of the pressure drop at five different flow rates covering a range of Reynolds numbers from 1500 to 7500 based on the header diameter, the bare case has often a lower pressure drop than the curvy case. Thank you for listening, and we may go to the Q&A session. Thank you very much.